Welcome. In this lecture, we will discuss how to determine the sample size for an experimentation. It is a very important concept, because sample size plays a significant role in the accuracy of the measures. We will cover this in two different lectures. In first lecture now, we will discuss with reference to single population mean test and difference between two population mean test. So, the contents of presentation today, we will see that how the sample size can be calculated using confidence intervals framework and hypothesis testing framework. You see this figure here, you just consider a normal population, single population with mean mu and standard deviation sigma. Suppose you have collected one sample of size n. Now, you are interested to know the confidence interval of mu from these sample calculations. So, x bar is the estimate of mu and x bar is kept here, and then you have found out 100 into 1 minus alpha % confidence, which will be from between L to U. And we have seen earlier L equal to x bar minus z alpha by 2 sigma by root n, and U is x bar plus z alpha by 2 sigma by root n. Now, this plus minus sigma or sigma z alpha by 2 sigma by root n means from x bar to U as well as from x bar to L, this is known as margin of error. Now, what we assume that the mu lies in between this interval with a confidence of 100 into 1 minus alpha %. We do not know that what is the distance between x bar and mu is somewhere. So, let us the permissible error is E, which is x bar minus mu absolute value. Now, we should calculate n in such a manner that this error lie within the margin of error. That means, the maximum error quantity will be m e. So, that is the concept. So, if I say then what is m e in this case? Z alpha by 2 sigma by root n. You see, sigma is the population standard deviation, it is fixed value, you do not have any control on it. Now, where you have control? You have control on n. So, if we say that E, which is the acceptable error, equal to, it will be maximum, it will be less than equal to z alpha by 2 sigma by root n, and using this you can find out n equal to z alpha by 2 sigma by E whole square. So, if you know sigma, if you then for a particular confidence interval, for a particular confidence interval means 100 into 1 minus alpha %, or for a particular level of significance alpha, you will be able to compute n, provided you know the E. Suppose let alpha equal to 0.05, then z alpha by 2 will be 1.96, and let sigma equal to 10, and suppose E the accept equal to that x bar minus mu, this will be acceptable one is this is 2. So, then what will be n? N will be 1.96 into 10 divided by 2 square. So, that means this is 9.98 this into 10. So, 9.8 square. So, this will be, if I say that this is around 10, then it is almost 100. So, this is the way you calculate sample size. Now, sometimes what happened in this confidence interval approach, you do not know what is the sigma value. In that case, you use S as the estimate of sigma, and then what you require, you cannot use this Z distribution, you will be using T distribution, and then n instead of Z alpha by 2 sigma by root n sigma by E square, it will be n will be T n minus 1 alpha by 2 into S by E whole square, where S is the sample standard deviation. Okay. So, essentially even if you say alpha equal to 0.05, then depending on this n, suppose you choose a particular n, these degrees of freedom will be different. Second n, like this degree of freedom will be different. So, you have to find out that n which ultimately satisfy the condition, then it will be. So, as T is T n minus 1, this quantity is again dependent on n. So, the formula what is written here as n equal to T alpha by 2 n minus 1 S square by E, this will only give you for a particular n what is this, you choose n, then T alpha by 2 and S by E, but you have to go for trial and error method. This is what we have shown here for T distribution. Here instead of single population, we have used two populations, and our test is, or we are interested in the confidence interval for the difference between two population means, like mu 1 minus mu 2. So, mu 1 is the population for population mean for the characteristics y, and this is for first population, this is for second population, and this will be the difference. So, we want to know the difference between two population means, whether they are different or not. Okay. So, we suppose we want the confidence interval for this, then you all know, we have seen earlier, this will be nothing but y 1 bar minus y 2 bar minus we can write T n 1 plus n 2 minus 2 alpha by 2, and then root over 1 by n 1 plus 1 by n 2, and S p will be there. So, this is plus minus, this is the interval. Now, if n 1 equal to n 2 equal to n, then this quantity become T 2 into n minus 1 alpha by 2 S p root over 2 by n. T alpha by 2 to n minus 1 S p root over 2 by n. So, here what happened, you see that what is the controllable, S p is uncontrollable for you, because this is the sample pooled variance. So, we have n which can be controlled. So, this n, now if we plot, that is T square root of 2 by n, and this side n, we will get a curve. The curve will be something like this, what is shown here. You see, we have plotted this versus this, and ultimately you see that when the n increases, this quantity decreases, and at around 10 or 11, after that there is not much decrease. So, we can assume that the n a 10 is a good sample size. So, notice that the curve descend rapidly as n increases up to about 10 and less rapidly beyond that. So, you can say n equal to 10 is a reasonable good sample size. Okay. So, this is what is our confidence interval approach. So, first I have given you for single population and for two population mean differences. If the random variable y1 bar minus y2 bar, this given situation it follows normal distribution, it is easier, or if it follows t distribution, then you have to choose n, then the degree using that corresponding degrees of freedom find out the t values. So, you require a iterative method whether it is a single population or two population case, and then you find out that n, you consider that n which gives you the less t square root of 2 by n. Okay. Now, we will discuss another approach called hypothesis testing approach. What you do in hypothesis testing? You assume some null hypothesis and alternate hypothesis, and under null hypothesis you test using appropriate statistic and statistical and sampling distribution, and then you reject the null hypothesis depending on the test result, or you fail to reject the null hypothesis. As a result, what happens? There will be scenarios, two are favorable and two are unfavorable. By unfavorable, what I mean to say that we commit certain errors, and that is what is the decision framework for hypothesis testing. Now, you see the suppose H0 for let it be a single population, H0 we are saying mu equal to mu 0, and H1 we are saying mu not equal to mu 0. So, this is what you have seen earlier. Now, the situation may be H0 is actually true and H0 is actually false, but your test may accept a false H0 or may reject a correct H0. So, that is the situation here. If H0 is true and your test accept it, then it is right decision. If H0 is false, test accept it, it is again right decision. But if H0 is true and you are rejecting null H0, then it is an error called type 1 error, whose probability is alpha. So, alpha is probability of committing type 1 error. That means probability reject H0, H0 is true. Similarly, another one, H0 is false, but you are accepting it, this is known as type 2 error, and beta is the probability of type 2 error. The beta equal to probability fail to reject H0 given H0 is false. Okay. Now, this is a very interesting one and very important one also, because if you accept H0 when it is false, and then you take many decisions which ultimately leads to very erroneous decisions which will be very costly also. So, another concept we will use here is power. What is power? Power is the 1 minus beta. This is nothing but probability of rejecting H0 when H0 is false. So, we will now show you the sample size calculation using this hypothesis testing framework. So, primarily we will be using either beta or 1 minus beta, and we will see that beta or 1 minus beta is a function of sample size n, and then for a particular beta or 1 minus beta, what we want to achieve then what will be the sample size n, so that that particular beta or 1 minus beta can be achieved. So, see the situation here. Situation is, if H 0 is true, this is the left hand side normal distribution. We are assuming Z distribution here. So, if H 0 is false, that actually mu is not equal to mu 0, that means mu is mu 0 plus delta, then this under this condition H 1 is true. So, then the underlying distribution is the right hand side one. So, how do we test? We calculate that Z 0, which is x bar or y bar, here we are using x bar minus mu 0 by sigma by root n. We are considering x is the variable of importance, or we can write Z 0 equal to, all through we have written this way, mu 0 by sigma by root n. So, if mu equal to mu 0, then what will be the expected value of Z 0 under null hypothesis? It will be expected value of either x bar minus mu 0 by sigma by root n, that is what you want to calculate. So, this is nothing but basically expected value of your if I just do little bit of manipulation, we will get what we are getting, mu equal to mu 0 plus delta. Okay. So, mu 0 equal to mu minus delta, then this will ultimately leads to expected value of x bar minus mu plus delta by sigma by root n, and then x bar minus mu by sigma by root n, this will be 0, that expected value of this will be 0, but expected value of this will be there. So, that means expected value of delta by sigma by root n, which is nothing but delta root n by sigma. So, if H 1 is true, then instead of this quantity x bar minus mu 0 by sigma by root n, or expected value of y bar minus mu 0 by sigma by root n, which one you take? You take y is the random variable or x is the random variable, depending on this will not become 0, this become delta by sigma root n. That is what is given here. So, that means the second distribution is normal distribution with mean sigma delta root n by sigma and variance is 1. Then what is the beta? Beta is your, you go back, what is beta? Fail to reject H 0, H 0 is false. So, that means what we are having, this is the distribution under H 0. So, but H 0 is not true, H 0 it is H 1 is true. So, any value falling here, what will happen? It will be, although H 0 is not true, but we will accept it. Then what is the probability that H 0 is not true, but it is accepted, is the overlapping portion between this and this, because minus z alpha by 2 plus z alpha by 2, that is the region which is the acceptable region. So, the overlapping portion under H 1 true is this shaded portion. This will, you find out this probability, and then you find out the probability will be like this. This is the equation probability. Now, in case that is not, your sigma is not known, you will use sample standard deviation, then this quantity x bar minus mu 0 by sigma by root n, this quantity follows t distribution, and your beta will be calculated using this equation. That beta will be probability minus t alpha by 2 n minus 1 to t alpha by 2 n minus 1. That means what happened in this case, this I have done several times. This will be minus t alpha by 2 n minus 1 and this will be plus t alpha by 2 n minus 1. So, beta will be your probability that minus t n minus 1 alpha by 2 less than equal to t 0 less than equal to t alpha n minus 1 alpha by 2 this. However, this cannot be because see here what happened n is there, but if when z is there, if it is z distributed, then we will write z alpha by 2 minus z alpha by 2, which is independent of, which is devoid of n. So, we require a curve like earlier I have shown you the t distribution time, you use a curve. So, this kind of curve, so beta is dependent on n. So, now beta versus n. Okay. So, as such what happened, we find out that from this equation that delta by sigma and beta they are dependent. So, if you plot beta versus delta by sigma for a particular sample size, then this curve is known as operating characteristics curve or OC curve. And or you can produce beta versus n also, that is also OC curve. So, we will see that two curves, one is beta versus delta by sigma, another one is beta versus n, or we will see 1 minus beta versus n, all are basically operating characteristics curve. The beauty of this curve is that given value of beta and given a value of for a particular delta, you will be in a position to calculate what should be the sample size, and other way around given delta and sample size what will be the beta. So, those alternatively you can calculate. Okay. So, now let us see that one kind of operating characteristic curve where beta versus d is nothing but delta by sigma, which is basically sigma weighted delta. Delta is what? That mu is not mu 0, mu is mu 0 plus delta, that is the mean shift. What is the shift in mean? That is delta. So, this when it is divided by its standard deviation by standard deviation sigma, then we are creating a quantity called d. Now, probability of not rejecting H 0 when H 0 is false, that is what is your beta versus d you will be getting for different sample size, it is like this, the curve is like this. So, you see if your sample size increases, then for even a small d you are able to detect it. Okay. So, if because a operating characteristic curve will give you the behavior with reference to beta and d and also for different kinds of n. So, probability of not rejecting H 0, beta is very high, suppose n equal to 2, even though d is very large, but then also what happened, the probability of rejecting H 0, probability of not rejecting H 0 is very high, beta error is very high. So, if you increase this, you find out that the probability of not rejecting H 0 is reducing. Okay. So, one may use this power curve. What is the power curve? Power curve here instead of beta we are using 1 minus beta versus sample size for different value of d, So, if you know d and you basically fix a beta, then from this curve you know the sample size. Okay. And here suppose if you know beta and you know d and fix a value of beta, then you or fix you want to see that the for a particular sample size what will be the beta, that is also possible. Suppose I know d equal to 1, my sample size is suppose let it be 7, So, 1 and sample size 7, what will be the probability of not rejecting H0? This you project to left hand side, it will be like this value maybe 0.38. In power curve what happened? We have here what we are saying that power is the is 1 minus beta, that means probability of rejecting H0 when H0 is false. Suppose our d value is 1, and then if our we want it to be that 80% power should be there, or for 1 minus beta is 0.8, then you may find out that it you require around 50 number of observations to be collected. That is what is your sample size. So, now what I will do, I will give you one example. Two competing medicine A and B are analyzed to determine how they affect the mean curing time. Each of the medicine A and B were administered to separate group of 10 young patients. The following results obtained. So, we are considering here that the 10 young patients, these two groups are similar in all other counts, except they are administered to different competing medicines. Suppose the medicine B produces a mean curing time that differs from the mean curing time of medicine A by 4 units, and if we want to reject H0 with a probability of at least 0.90, what is the sample size required? What are the things given? Y1 bar, S1, Y2 bar and N1, and Y2 bar, S2 and N2 is given. In addition, what is given? The difference is 4, not 0, and in addition what is given, that we want a probability, we want to reject H0 with a probability of at least 0.90. So, what is the sample size that is required? We want to know the n, whether the N1 10 and N2 10 is sufficient or not. So, first you calculate SP, which is 2.06, then you find out delta is here almost 2. Now, from the chart, as beta is 0.90, beta 1 minus beta is 0.90, because probability of reject H0 and H0 is false, that is 1 minus beta is 0.90. For d equal to 2, what value we are getting from this? So, d 2 and 0.90 is 1 minus power is 0.90. So, if you just what you do, if you take this is 0.90, take a horizontal line here, it meet here, and then draw a vertical line, it will be somewhere here, whose value is around 14. So, that means n should be 14. So, now we have two different two populations. So, it will be for each population, each sample, it will be n by 2. So, N1 equal to N2 equal to 7, roughly n by 2 will give you the accurate results. Okay. So, this is what the sample size determination. So, you can use the confidence interval approach, or you can use hypothesis testing approach. And in hypothesis testing approach, the important concept what you run is OC curve, that is operating characteristic curve. Okay. And OC curve is developed for different combination, like it will be beta versus the shift, mean shift, or for given n sample size, beta versus that n for given shift, power versus that mean shift given n, power versus your n given mean shift. Okay. So, it is a very popular concept. I hope you will be, when you conduct experiment, you will be in a position to know what should be the appropriate sample size when you are conducting experiment involving one population or two population cases. Okay. Thank you very much.